Okay, class, let's try this. Um, so this part of the lecture is for January 31st, missing class due to the weather conditions. And the topic we're trying to cover is to look at the response of linear time invariant systems. Um, and the goal is that given any natural condition and any external input signal, we want to be able to find the corresponding response of a linear time invariant system. And this is accomplished by decomposing the total response of a linear system into two parts, the zero input response and the zero state response. Okay. So we have done this last Thursday, and for example, for the zero input response, we started zero state but wasn't able to finish. So let's first have a quick review of what happens to zero input response, meaning everything will be caused by the natural condition. So a general form of a differential equation is usually used to characterize the input-output relationship of a linear time invariant system like this. Okay, this is what we have. And you have also this in the textbook. And the highest order of derivative in this equation is the one on the very left right here is of order n, so we use n to denote also the order of this differential equation. Okay. Then for a particular example, this is the one we discussed in class, d2 y dt squared plus 3dy dt plus 2y. And this is typically the amount of calculation you will face, let's say, in your exam. So for this particular system, you need to be able to figure out the following. First of all, this is a second order system, meaning n equal to 2, the highest order derivative you see in this equation is 2. Okay. Then you can map all the coefficients, okay, those a's and b's, to the actual numbers given in the example. For instance, in this one, a1 equal to 3, a0 equal to 2. And for the b's, for the input signal coefficients, it's a little tricky. Now, in the example you see above, you have this bn dnf dtn term. Since n equal to 2 in this example, you'll be looking for this term, b2 d2f dt squared, which you don't on the right hand side. That only means this b2 term should be equal to 0, and since 2 is actually n equal to 2, so this b2 actually will be the bn terms that you will use in the unit impulse response calculation. For b1, b4 is easy. We can easily find out them through this equations. Then some of the input response, zero input response, will need the following four steps. First, solving the differential equation. Second, solve the characteristic equation to find the roots of all these lambdas. In this example, lambda, the roots will be -1, -2 from this quadratic equation. Then if all roots are distinct and real, you'll be able to express the zero input response in a simple form. So it will be the sum of a bunch of exponential signals. If the roots are repeated or complex, you have other ways to handle them. You have two examples in the textbook, and in the homework this week, you will need to use, you will be asked to do this by yourself. And when you have this general form, the only thing that left to do is to solve for the undetermined coefficients C1, C2 up to Cn's. In this example, you only have C1 and C2 to solve. And to solve for them, you need to use the initial conditions. Okay, so you plug in the initial condition of the output signal at time 0, and for this case, you need two equations to solve the two coefficients. So the other equation is given by the initial condition of the derivative of the output signal at time 0. So you put two together, solve for C1, C2, and plug them back in the equation. You will be able to figure out what is the zero input response. And that is all for this particular part.